right, last talk before our break will be by Elena D'Onghia on Galactic Chronicles, Unveiling the Milky Way's Merged Past.
Thank you very much. I'm very honored to be here among so many distinguished alumni at the ITC, and it's always a pleasure to be back. And before I start to tell you about my more recent work, I want to just summarize in this picture what my work was at the ITC. So it's basically, it was all about spiral disks, processes that are shaping the disk eventually for the Milky Way. And when I left the ITC, started really, coming Gaia. And so I think, my research really benefit from being here, where I grew as a scientist, but also where I made friends. So I started collaborations that remained for a long time, and it's my pleasure. Really, I had the pleasure and also the privilege to work with Lars Hernquist, which I'm very grateful to, because here is where I really got the passion for galactic dynamics, and since then became actually my focus, the main focus of my research. So I'm very grateful to this place. That was just my starting of my talk. Now I hope that this little introduction will show you how much my research has been shaped from being here. And I just want to tell you something about my recent work with a student. It's Lakshmi Tulasindaran. She will be visiting here in the fall, the CFA, and she's doing something really interesting about the Milky Way. So we know, because we have seen, in all the simulations we learn from cosmological simulations, how it's true that, halos are assembled, including the Milky Way, by dwarf galaxies and by accretion, of material over time, across time. So I think here has been, shown since decades now, how the lambda CDM works. But I think that in terms of data, it's still very hard to be conclusive about the merging history of the Milky Way. Let me tell you a little bit more in details what I mean about this. So usually when we look for, printings or fingerprints of mergers in the data, we look for kinematics, so stars that have similar velocities, or we look for also, or we combine chemodynamics. So we look for, stars that have more or less the same metallicities. So in order to try to understand where the fingerprints or the signatures of mergers. And, in the past, have been used Gaia, Sloan 4, Apogee, Gala, Lamost. They're giving us all observables, and people try to infer in a very beautiful way, what the merging history was. However, these observables are not conclusive, because it's very hard to say exactly, to have a blueprint in one picture about, what happened to the merging history. And we have seen also, theoretical work, how difficult it is to try to infer, the merging history of a galaxy. So, as an example, I think this is the beautiful work came out with Gaia from Amina Helmi at the same time of Belokurov. They used kinematics to separate the stars from the halo. On the left in the data, it's the blue stars, from the stars on the disk. These are the grays. And on the right, they made the point in pointing out that the Milky Way had a major merger a long time ago, the Gaia and Enceladus structure. They made a point using the simulations and showing when you have a major merger, you can form signatures. We can form stars with similar kinematics or metallicity. However, the time of this last major merger is being debated still. So some groups think that, because on the uncertainties, on metallicities and uncertainties, so it's still unclear if it's 8 gigayears, 12 gigayears, when exactly happened. This is why I want to show you basically another idea. So we propose now another observable that could be maybe more interesting to get a blueprint of the Milky Way merging history. So we use here, so Lakshmi has used, all the catalogs available. So she used Red Giants, Red Giant from the Lamoste. She used the metal pulse stars from the Sloan 12, the Sloan 4, the Apogee, and the Star Horse sample from Chiappini. So everything we could find available in the, publicly available to the community. And of course, she correlated with the Gaia EDR tree, all the stars. And basically the sample that we use is from Lamoste, almost 1.3 million stars, from the Star Horse, around 250 and 100,000, 50,000, 100,000 have ages, and the error on the ages are around 25-30%. So then she selected all the stars that are between 8 and 12 kiloparsec in the Milky Way from all those samples, and that they go above and below 3 kiloparsec. So basically to try to, to figure out the stars in the disk or at the edge of the disk. So at the end, we used almost 1 million sources to do this work. And here is what comes out. So this is the data in the Milky Way. So this is a work also with Bob Benjamin and Ron Drimmel and Eloisa Poggio. So here is basically on the y-axis, it's the dispersion on the vertical height. So she used for all the stars, she checked the vertical height, and she plotted here the dispersion over the thickness. Basically, it's a proxy of the thickness of the stars in the disk. And then as a function of the x-axis, it's actually the age. So she binned the data in 750 beans in age from the available data. So what you can see here is that there are basically peaks. So now we know that when there's a major merger, a merger event, we are expecting that the stars gets heated up, and so they will go and will eventually form a thick disk, and that's of course known. So it's expected. But when we look at the data here, we see that there are spikes and then decrease in the quantities of the dispersion of the thickness. So we look at now what it's very useful from the ITC. We look at in the TNG50 in order to get some guidance about what's going on. So we checked, we took basically galaxies that are more or less Milky Way analogs, similar mass, and we look at what happens when you have a major merger and treated the galaxy in the same way we would treat the data. Because we have ages, we have all the properties that you have also in the Milky Way. So in this specific example, for example, between 6 and 10 gigayears, this galaxy is going to have a major merger in the TNG50. And so we look at what happens to the dispersion on the Z components, on the thickness. And we see that there is a spike. So the reason for that, so there's basically a peak in the delta Z versus age, and then there is a decrease after the major merger. So what happens is that basically it's easy to look at into the simulations as a guidance. So it happens that the stars get heated up, they are heated up, but also there's a readjustment in the disk, or there's new fresh gas coming in, and so new stars are formed. So we also checked, other cases where we have minor mergers, basically, or flybys, mostly flybys. And these are other other subhalos that are coming from the TNG50 at the bottom, at the top, on the left and the right. And you can see on the left, it's actually flybys from a satellite in ID that, gives that insights about. And we see also, a peak, although it's not as sharp as in the case of a major merger. So if we put together, the guidance from the TNG50 and the data for the Milky Way, we might have found actually something very interesting. So there might be two events. So first of all, we can probably, within the uncertainties of the ages, we are still working a little bit on, exactly giving, how much robust is the result given the ages. But there seems to be two peaks that happened, a long time ago. So eventually there's a first peak that might be something before the GSE. So there are people who have pointed out that Kranken, it's probably a merger before the GSE. Then there's probably the GSC around 10.5 gigayears. And then there's other three little peaks that eventually are the passages. They seem to be consistent, maybe with the passages of Sagittarius. So if this is true, of course, it's very interesting because we can, first of all, we can date, when the mergers happen in the Milky Way. And we can also propose an observable that could be used as a way to have in a blueprint the merging history of a galaxy. And it's a much direct, observable for galaxies. In this case, if you have enough data for the Milky Way. And so, right, the other thing that I think it's interesting to notice that maybe this work could highlight is that we actually find when is the time that the transition happened between having a thick disk and having a thin disk. And it seems that might be 10.5 gigayears. It might take another 1.5 million gigayears actually to settle the thin disk into the Milky Way. And so, that's basically the contribution of this work. Before I stop, honestly, I wanted to also tell you something a little bit maybe will amuse Avi. And it's about maybe boundless ideas, or let's say, ideas without boundaries. So yesterday we had this discussion, and I think this nice lady showed or mentioned the NIAC. So there's a branch in NASA that it's less conservative, and it's actually the NIAC. It's basically the NASA Innovative Advanced Concepts Award. It's an award for ideas, futuristic, very breakthrough ideas in aerospace, especially for missions, also for astronomy. If you have ideas for telescopes. And I don't know if you have seen, so I've been awarded 2 years ago a NIAC, and I'll tell you a little bit about. And it's really, it looks like, to see ideas from Star Trek or something like that. And the NASA gives not much money for the feasibility of these ideas, but gives you the money to really develop something that it's absolutely out of the box, but that has a vision. For example, this is what really impressed me a lot at the NIAC. So they are doing habitats with fungi. So the idea is that they take the mycelium and they put the water in the mycelium, and the fungi becomes like bricks, and they are so almost as hard as concrete. But they have the advantage, basically, that they can take the shape of any habitats, so they can create, inflatable habitats with these fungi, and the fungi have the ability to basically to shield the habitats from the UV radiation. So they're thinking about this for the moon, for habitats on the moon. So that's just to tell you how crazy these things can be. And I only take a few minutes to tell you what we have been awarded for. So we had this idea, and we only proposed the idea, and now it's up to the engineering department really to see if it's feasible or not from the structural point of view. So, there's always a problem if you go into space with cosmic rays. Now, as scientists here, we study the cosmic rays, and we've seen these beautiful, simulations that are looking for the properties of cosmic rays for galaxies. But for our species, for humans going into space, it's a problem. And so this is the problem number one for space travels, and maybe Elon Musk forgot about this, but it's really, really important, just even on staying on the moon. And so, so what we did was just to use a simple idea is, to basically to develop a magnetic field, an active magnetic field, so around the spacecraft, using the Albach configuration, which we know from physics. It's one of these configurations when you basically put the magnets, misaligned of a certain degree, and the advantage is that it creates a magnetic field outside, but a null magnetic field inside some volume. So in this case, on the spacecraft, it's a bit inspired to the Earth magnetic field, but it's not quite the same because the Earth has a dipole, so it has a very low magnetic field but very extended, so it's very powerful in shielding cosmic rays. This one is not as powerful, but at least it could give some shielding. And we did just this little model, using a code that can just shield the trajectories of cosmic rays, and we showed that we can basically shield up to 50%. And so that was why it was awarded. So now we have a team also at the mechanical engineer department at UW. And so I have this aside project after tenure that I'm actually still pursuing. And so I don't know how far we will go, but I wanted to amuse Avi about boundless ideas. And I just finish. For me, the ITC, it's, as I said, it's not only the place where you can grow, but for me, it was also a kind of a new environment where you can imagine the unimaginable, and you can be innovative beyond, the conventional, because that's what people have shown me here. And thank you so much.
All right, that's a great way to go to coffee. Let's have some questions.
Awesome talk. I really love the magnetic field idea. Are you sure you didn't steal it from Star Trek? They had magnetic coils. I'm a nerd.
No, we've been awarded. So it seems that it might be feasible, but there's many levels of feasibility you have to pass through. We just are on phase 1. So
I have a science question, a real one. In your plot of the spikes, if you compare to, let's say, the TNG, can you get an estimate on what should be the mass ratio of a minor merger coming in and creates this type of spikes? Or flipping the question is, how big does a satellite need to come, either through a flyby or crossing the disk, in order to excite the vertical disk?
I think the satellite that Lakshmi looked into, they were similar to Sagittarius. So let's say 1% of the mass of the main galaxy. Closer it is, probably higher is the impact. She hasn't looked at all possibilities; she just found something very tailored to what the problem was. But definitely, the disk seems to be very susceptible to this.
Thanks.
First, Elena, I wanted to congratulate you because the first time I saw a beautiful simulation of a galactic disk was when you showed it to us with all the holes as a result of instabilities in the disk. And now the Webb telescope shows things that are extremely similar to what you predicted. So congratulations for the success of that. My question has to do with actually the innovative idea that you had is very important, because that's one thing that Elon Musk doesn't understand. He keeps talking about going to Mars, and it's very risky on the surface. We have to go to a cave if we want to protect ourselves. But you're suggesting a more practical solution with a magnetic field. When you say half of the cosmic rays are blocked, probably the half that is not blocked have the higher energies,
yes,
right? Those are the ones
true.
that have a Larmor radius that is big enough to penetrate. So aren't those the most damaging to the human? Because my understanding is that within a few years, a significant fraction of the cells in the human brain would be damaged without protection. So it's really a big health risk.
Yeah, it is. I have this slide that I didn't have time really to talk about. But so there's two kind of, as you said, two kind of particles. There are the solar wind particles coming from the sun. They are low energy. So those are also quite shielded by passive shielding. So if you put aluminum thick enough, you can also shield a good fraction of those. But definitely the magnetic field will help also with a bit higher energy. They are less frequent, the very high energy cosmic rays or the IZ ions, but they are very harmful. It does not shield them completely, but we are really trying to optimize now. The engineering are trying to do it in a configuration that could, always based on the Halbach array, but they could optimize, that shielding. So it's really the high energy, although it's very difficult to shield the very, very high energy. Above the 1 GeV, it's actually hard even with the magnetic field. So the best shielder is actually water or hydrogen, but water is too heavy. So this problem, it's only for physicists the beginning, but for the engineering, the engineers, the problem is how to make something that's also light. And we are trying to see, how much we can exploit the idea. But there's not much on the market. And because NASA, and going back to the second question of you, if you, so basically NASA puts a limit for the career of an astronaut on space. And this limit, it's actually only 600 millisievert, which sievert is, is basically the unit that is being used for absorbed doses of radiation on the human being. And so, to go to Mars, it's basically already for a round trip, but even for one trip, it's already the excess risk for an astronaut to go. So, and as you said, there's a risk for damages, in the brain for sure, but also cancer. I mean, it's like to do radiotherapy all the time. And so it is the problem number one for NASA. NASA looks for solutions. Right now, the only solutions that have been found is passive shielding, vests, but they are not, they don't really, so these solutions are not really helping. So until we don't find the solution, will be not possible to have actually a trip to Mars. And NASA, until, we'll never send, Elon Musk can say whatever he wants, but he can't go to Mars without NASA saying, yes, we are now, at the technology ready enough to really fly, for such a long trip for humans. So, but it's a problem number one. And to me, I know everyone is excited by planets, sure, exoplanets, finding life, but what about curiosity of the human being? What about going, out of the village and look at another planet beyond the moon? I think that's also, something that should be pursued this century. Yeah.
Really nice work, but I'm gonna go back to the galaxies stuff. Sorry. So we just saw the last talk by Carl. We saw these movies with the fire simulations where you have this bursty star formation, and then the thing settles down and you get a nice thin disk. If you follow the stars that were made during the bursty period, they end up being in the thick disk. So how do you distinguish mergers from bursty star formation? Is that possible?
I think here you distinguish. So the thickness will tell you, how much is the velocity dispersion, how much they go, above or below the plane. But the age will tell you how young they are. So it seems that the very old ones are the very metal poor, are the very old one are the ones very in the very thick disk. The other one are not necessarily in a thick disk. They're just, you can see that there's a sharp decrease. So
yeah, and what I'm saying is that the old ones in fire are made through bursty star formation, not mergers.
I see. I should look at in fire, how much is the peak that they have, how much, this is based on the TNG50.
So
which actually was an amazing guidance because it helped us to interpret it. Because I was not expecting this. You expect that you form the thick disk, then you're not thinking that maybe you have a sharp decrease. So it really was, it was actually, I haven't looked at it in the fire.
Okay, thank you.
Hi, Elena, awesome talk. I actually have two questions. So one is a follow-up to this. So if it's a burst of the star formation, would you expect like more stars formed at this ages? So did you look at the distribution of ages? Do you see like corresponding features there?
In the simulations, you mean?
In the Milky Way.
No, in the Milky Way, this is everything we found.
Right.
So these are all the data between 8 and 11 kiloparsec.
But I mean the PDF. So if there's like an excess of stars at around ages of 10.7 and 12.3 or whatever.
Oh, if this locally there's a...
Yeah, like if
no,
there are like
it's a good
bursts.
idea.
Yeah.
We can check that.
I don't know about the old ages, but there was a circulation history of the Milky Way that shows peaks at like consistent with Sagittarius.
Yeah, there's a recent paper, right?
It was like a few years ago from Apergy. So at least for the kind of green peaks, I think they're actually corresponding.
Okay.
I'm not sure,
Yeah, it's not clear which way.
But there was a measurement
I think that, yeah, there's also recent work, I think, on Nature Astronomy about the star formation. It seems consistent.
Yeah,
So
okay.
this peak seems consistent. I think the novelty here is that we put everything together now, the
Okay.
young and the old. And it seems that you have, a merging history of the Milky Way in one plot.
Okay. And another quick question is whether these two peaks, can it be consistent with two passages, or is it for sure two separate events?
Oh,
The
okay.
two
We
peaks
interpret it as it could be anything. We interpret it as the multiple passages of actually Sagittarius. The old one. Oh, the old one. We are now before submission. We are almost at the time of submitting now. We are debating if these two peaks is only one or not. Honestly, if it's two peaks. And if we can say something conclusively about that, means that before the GSC, there was another merger, eventually Kranken, they called it. So that would prove it. And even the time will happen. If it's only one peak, then it's just that, it takes a while to have the major merger, according to the simulation. So it could be consistent on the GSC, being from 12 to 8.5 to 10 gigayears, 10.5 gigayears. But it would give this plot would give you when it happened. So it would exclude these works that are saying that it happened 8 gigayears ago. It seems to be actually older than that, if that's correct.
Okay, great. So we have a good time, I think full 30 minutes for our break, and we will come back here at 10 after the hour for two last talks before lunch. But let's give Elena and all the speakers another round of applause.